Da-da-da-da-da-da-da-da. Wrong game. Okay, so what we're going to talk about is the mirror equation right now. And in the mirror equation, it's kind of a derivation to get there. It's a lot of geometry, so try to bear with me. But in the end, like once we get the equation, that's what we'll need. But I'm going to show you where it comes from. So let's start with a concave mirror, and let's draw a principal axis running through the center of it. There we go. And then naturally, we'll put our focal point somewhere. So it's on the concave side of the mirror. So here's our focal point. Bloop, bloop. And let's also put our center of curvature somewhere. Remember, the center of curvature is twice the distance from the mirror as the focal point. So I'm going to take my two fingers, put them up to my screen, and then kind of double this up. So I'm getting my center of curvature is about here. These are rough drawings. I'm not using a ruler like I should be because we're all doing this digitally. Yay, COVID-19! But, you know, this would be nice and precisely laid out. And then what we're going to do at this point is let's draw in an object. So let's take an object and let's put it between the focal point and the center of curvature. So here's going to be our object right there. And let's call the bottom of the object point O. And let's call the top of the object point O prime. Okay? Now, this object itself is going to have a height. So let's call this height of the object HO. So we've got our focal point, center of curvature, an object, the bottom and the top of the object, O and O prime, and this is the height of the object, which we're going to call HO. Now, let's try to just figure out from a ray diagram where our image will be located. Well, when we do this, the first ray that we're going to draw is from the top of the object, going flat, striking the mirror, and then we know that this mirror strike is going to come through our focal point. So I'm going to try to draw this as best as I could. If I had a nice sheet of paper here and I was drawing this to scale and whatnot, I'd take a ruler and line it up. But we should get a ray that kind of runs like this. Should go from here and should come nicely through the focal point out to infinity, just like that. Okay, so that's a great line. Second ray that we like to draw goes from the top again. It goes through the focal point, striking the mirror. Boom. And then at this point, we go from out here, where we struck the mirror, and then we come flat. So it's just the opposite point that we drew before. So let's draw that flat, bing. And then that means that our image will appear out here on the tip, because that's what we went from the tip, and there is our image, okay? A few things we know about this image immediately. It is a real image because it is inverted. Anytime we invert the object, we become a real image. I can't write the word real for some reason. Real, there it is. And notice that it has become larger in this case. We're going to label our image as well. Let's call the image down here I, and let's call the tip of the image I prime, just like we did O and O prime before. Okay? Now, there are a few other things that we're going to label here. We know that if we think about this concave spherical mirror, if we kind of think of it as a very shallow curvature, the tip here and the base, we're going to say are actually in the same plane. So right now it looks like they're in different locations, but they're not. This is a very shallow curvature. So what we're going to be able to say here is that this focal length is some distance between the mirror and the focal point. This right here is an object distance, which depending on what kind of book you're using or what teacher you have, this might be a P or it could be an S naught. We're going to call it DO for the distance of the object. And that means all the way out here to the mirror, this is the distance to the image. And like I said, this could be a Q out here, or it could be SI for an image distance. Really depends on what book you have, but just recognizing we have a focal length, a object distance, and an image distance. Those are the big things, okay? Now, why is this so important? Well, like I said, this is a very shallow mirror. So if I bring this down, the center of the mirror point here, if I bring this down, this extra distance right here doesn't really exist, or it's so small that we don't care about it, okay? We're going to pretend this mirror, while it is curved, it's like, it might as well just be straight up and down, okay? And if we call this point back here point A, that means we'll call this point down here point B. And what's nice about this is if we consider this to be relatively straight going down, it starts to open up a lot of triangles for us, which allows us to do mathematics nice and easily. What we should be able to see, if we kind of sketch this out initially, is that if we go from O, if we make a triangle here, like this, this triangle that I just built from O prime to A to O, that triangle is actually a similar triangle from I to A to I prime. So these two triangles in this like bright garish, whoa, that is the wrong line, and this bright garish green right here, these are similar triangles. And that makes sense because this angle has to be the same because there is one more ray diagram line we could have drawn. We could have hit this corner or the centerpiece right there, and then the angle of incident and the angle of reflection have to be the same. So these two triangles will be the same. So we know that O prime AO and I prime AI are similar. And when we say similar triangles, what we do mean is that the angles of these triangles are the exact same. One is just scaled up larger than the other. So if you had a 3, 4, 5 triangle, a 6, 8, 10 triangle would be the exact same. It just got scaled up a little bit. Everything got multiplied by 2. So these triangles are the same. They're just scaled up. Okay? Because of this, we can state the following. If this object has some height h, then the image is going to have some height I. And since these are similar triangles, that means that this is just a ratio here. And the ratio of these heights is actually equivalent to the ratios of the distances. Because if the distance is doubled, that means the heights would double. Just like up here, the 3, 4, 5 became 6, 8, and 10. If the 3 doubled, that means the 4 has to double and the 5 has to double. They all have to scale at the same amount to be similar triangles. So what we can say then is, look, however our distance ratio changes, our height ratio has to change as well. What this allows us to state is that the magnification is equal to the height image over the height of the object. That's how we can magnify an image. And this is going to be equal to the negative of the distance of the image over the distance of the object. This negative here, this is a convention. This is negative because in our case, if we take a look at this, our magnification needs to come out as a negative number because not only did we get bigger, but we inverted, okay? When your magnification equals a negative number, you have gone inverted. You have flipped the image, which we did here, right? We went from upright, we're pointing up, to now we're pointing down. We're bigger, the magnification is greater than 1, and it's negative, meaning that we flipped, okay? So if you have a negative number here, you're inverted. If your magnification is greater than 1, you have become larger. If your magnification is less than 1, you've become smaller. And if your magnification equals 1, then you are the same size. Nothing's changed. Okay? So that's the first thing we can see with this triangle. And with this concave mirror setup, we can get magnifications pretty simply. Okay, so that's our idea of magnification. Now what we can also get from this very complicated ray diagram we've got going on with a billion different colors is we can also set up what is known as the mirror equation. And we're also going to see this equation for lenses later as well, so it is an important equation. But let's figure out just what we're going to get here. So we're going to create kind of a weird little setup here. If we look at O prime, F, B, and I prime. So we're going to take a look at these points. O, F, B, which is technically right here, but it's like also back here. It's a straight mirror that's curved. And I prime. We can create the following. We can create this triangle right here. And we can create this triangle right here. Now, why do these triangles matter? Well, if we look at this, the distance between A and B here on this like straight curved mirror, this is the height of the image. You know, I just took this left side here and I moved it over to the right. Well, this kind of looks like a weird little bow tie, right? It kind of looks something like this. And if we take a look at that, we can get information out of this. Since we know that this distance from here to here is the focal length, so like this is the focal length right here, and this is the height of the image, we can relate that to this triangle, where this is some distance and this is the height of the object, because these technically have to be similar triangles as well, because this angle, through some interior angle mumbo jumbo geometry thing that we may or may not remember, those angles are going to be the same as well. So these triangles here in red, those are similar triangles. And what we can get out of this is we can say that HI over HO, the height of the image and the height of the object, those can be equal to the distance between the object and the focal point and the line from the focal point to A. So if we go from the object to the focal point, that's up here, and then the focal point to A, that's down here. Well, this is really saying that what we can do here is this is the distance of the object minus the focal length over the focal length. And this has to equal, because of this ratio and this ratio, we can say that this in theory would be a similar ratio of, well, here, hold on, I messed that up slightly. This is an HI over HO. This is HO over HI, get with it. HO and HI, that's much better. We can say this ratio then is DO and DI. Dio Branda. So this, due to another similar triangle setup, we can get this thing here, okay? And if we run a little bit of algebra on this, which is always a pleasant time, but if we run a little bit of algebra on this, we should be able to quickly see that we get the following equation. If we take each side and divide it by DO, so we'll have a DO and a DO here. What we're going to get is DO over DI DO, DI DIO equals negative 1 over DO plus 1 over F, and then, you know, if these cancel out, this is actually just equal to 1 over DI. So what we can say here is that 1 over F equals 1 over DI plus 1 over DO. This is the mirror equation, okay? This is the mirror slash lens equation, and it is the important equation that we're going to need moving forward. 1 over the focal length equals 1 over the image distance plus 1 over the object distance, okay? It's super important that when you're looking at this equation, you be very careful, because notice that all of the values, they're in the denominator. they're all in the denominator. This is another one of those like, I'm adding resistors in parallel where I have to be like 1 over this plus 1 over that and then reciprocate it at the end in order to get back my answer. Okay, so that is the equation we want there. We want this mirror lens equation, and we want this magnification equation that we saw before at the beginning of this video in order to mathematically say where our objects are, so we don't have to keep drawing them, and how large they are, and if they're real or virtual. Okay, so these are two very important equations for this unit, and in our next two videos,